All right. Good afternoon, everyone. My name is Maxime Chambonneau, working at the Institute of Applied Physics in Jena, Germany. And today I'm going to talk about how paramount it is to take into account microfilamentation in semiconductor metal ultrafast laser welding applications. So, joining materials is essential for additive manufacturing industrial applications. If you want to build a complex device, you might use traditional methods such as adhesive bonding, brazing, anodic bonding, and so on. However, those methods usually show some important drawbacks. For instance, they may require another material or pressure assistance, or maybe the two materials will face some aging or degassing problems, or they might be just not resistant enough to high temperatures. As a very nice alternative, the laser welding technique has been developed. It consists of energy deposition at the interface and provides a fast, clean, and contactless way to join two materials. Noteworthy, it has been shown to be applicable in different material configurations such as glass-glass, glass-semiconductor, glass-metal, polymer-polymer, and more recently, ceramic-ceramic. However, in the semiconductor metal configuration, there is nothing too convincing so far. So let us have a try. To do so, we will illustrate semiconductor metal laser welding with silicon and copper, and we will employ the following arrangement, which relies on 9.8 picosecond laser pulses at 1.55 micron wavelength, for which silicon is totally transparent. Then we adjust the input pulse energy by means of a half-wave plate and a polarizer before the beam is focused at the interface between the two materials with an objective lens. This objective lens is also used in a customized microscope working in dark field and in reflection, which enables us to position the geometrical focus with respect to the entrance surface of silicon. And then the bonding quality is evaluated post-mortem by separating the two samples with an indenter. So if we try that and fix the input pulse energy to 300 nanojoules, then the shear joining strength is 30 kilopascal. Okay, and then what if we double the input pulse energy and go to 600 nanojoules? Then the shear joining strength is 10 kilopascal. That's weird. But the main question is that sufficient? And sadly, the answer is no. I mean, the samples are easily separable by hands with those shear joining strength, and the typical values for other material configurations or traditional bonding methods is on the order of 1 to 20 megapascal. So how can we explain this? If we want to answer this question, we have to keep in mind that silicon is a medium where the propagation is extremely nonlinear. And this originates from the nonlinear refractive index of silicon, which is about 100 times higher than the one of fused silica, for instance, meaning that self-focusing will occur at relatively modest peak powers. This implies that there is a competition between Kerr effect on the one hand and plasma effect on the other hand. In other words, a filament is formed, which has two major consequences. First, as illustrated here, there is a saturation of the intensity reached inside silicon below the breakdown threshold. Second consequence, as illustrated here, there is a nonlinear focus shift. And taken together, those two consequences lead to the conclusion that there is a strong depletion of the energy deposition at the exit surface of silicon. So what solutions can we propose for achieving semiconductor metal laser welding? Well, first, we will of course use an interface with a metal, meaning that the absorption is increased, which is good. And second, we propose a filament relocation at the interface between the two materials, meaning that the intensity will be increased. But to do so, we need for nonlinear propagation imaging. And this is exactly what we did. We imaged the nonlinear propagation inside silicon by means of the arrangement depicted here, which allows us to determine the 3D fluence distribution inside silicon. and thus the nonlinear focal shift as a function of the input pulse energy. On this data here, you can distinguish three different regimes. The first one is the linear propagation regime, which has been confirmed by point spread function analyses with our in-house tool, which is open access. If you want more details, please check out those two references. Then for intermediate input pulse energies up to 100 nanojoules, you can see that the focus is unambiguously shifted upstream the laser. However, the overall shape is conserved. And then for very high input pulse energies, you can see those focusing and defocusing dynamics, meaning that we entered the filamentation regime. So to conclude on these, well, increasing the input pulse energy leads to an energy deposition which will be far from the interface. In order to theoretically predict the behavior for the nonlinear focal shift as a function of the input pulse energy, we have developed a semi-analytical model relying on this equation shown here, where delta z is the nonlinear focal shift, f star is the effective focal length from the entrance surface of the silicon sample, which is nothing else than the sample thickness, and z and L for nonlinear represents the effective focal length associated with Kerr effect, which is considered as a lens. ZNL is further defined by Marburger's formula in this equation here, where K0 represents the wave number, A0 represents the beam radius at the entrance surface, PCR is a first fitting parameter, and it is the critical power for self-focusing, and P is defined here in this equation on the bottom. It is the reduced peak power at the exit surface of the silicon sample, where P0 is the input power, and beta 2 star is a second fitting parameter, which is the 2-photon absorption coefficient defined for A power. And with this two-parameter fitting procedure, we can compare some calculations to the experiments, and as you can see here, the trends are very well reproduced, meaning that the major physical mechanisms that are responsible for the nonlinear focal shift are correctly described. Moreover, we have carried out additional experiments with another pulse duration here in blue. The pulse duration in this case is 860 femtosecond, and well, the results are essentially the same. I mean, the trend are also well reproduced, meaning that our approach is benchmarked. Alright, so now that we know the behavior for the nonlinear focal shift as a function of the input pulse energy, we can come back to our initial problem concerning ultrafast laser welding of silicon and copper. Here in this figure, it is represented the shear joining strength for two different input pulse energies, without in red and with in green delta Z precompensation. And the striking feature here in this figure is that precompensating the nonlinear focal shift leads to a much better welding. Okay, so now what if we increase the input pulse energy and at the same time keep this precompensation strategy for the nonlinear focal shift? Well, the results are essentially shown here in terms of shear joining strength as a function of the input pulse energy, and one can see that it is possible for around 1 microjoule to reach a shear joining strength of around 2.2 megapascal, which is suitable for applications. And the reasons for this success is that precompensating the nonlinear focal shift delta Z leads to an enhancement of the maximum fluence reaching the interface, and simultaneously it leads to an enhancement of the energy reaching this interface. Noteworthy, indicated in purple here, one can note that there is no welding possible for input pulse energies below 100 nanojoules, which means an important thing. It means that Silicon and copper ultrafast laser welding is solely achievable in the filamentation regime. Ultimately, we have carried out material analyses of the welds. So first, concerning the copper sample, we have noticed the presence of silicon stuck to the copper sample even after breakage, here in white, which may indicate the presence of covalent bonds. Concerning the silicon sample, we have noticed the presence of nanostructures between the lines corresponding to the scans, which may indicate the importance of plasmonic effects during the welding. We have also done some Raman spectroscopy measurements, first on the copper sample, and we have observed a peak looking like the one of silicon, except that it is shifted, which may indicate that these silicon parts here in white are strained silicon. And finally, on the silicon sample, the Raman spectroscopy measurements revealed a broadening here in red of the Raman spectrum, which may indicate a partial amorphization of the material. It is worth noting that even if during nonlinear propagation imaging no damage is formed, silicon is modified during the welding. And this may originate from an absorption enhancement due to the free electrons in copper, and also a possible field enhancement due to the air gap through a Fabry-Perot effect. To summarize, we have demonstrated the first semiconductor-metal ultrafast laser welding by characterizing picosecond laser filaments inside silicon. We have achieved megapascal shear joining strengths that are compatible with applications, and if you want more details about the whole process, please feel free to scan this QR code, which will lead you to our latest article on this topic. Alternatively, you can also contact me at the following address, and I would like to thank you for your attention.